Hey folks, all right, time to move on to the subroutine level of optimization where we're looking at an entire procedure or entire function and trying to perform optimizations that make use of all of the information related to that. So now we've got a more complete picture of what's going on, right? We can go through and try and identify how all of the different blocks tie together and what information is generated in one and used in another. So again, data flow analysis is going to come into a lot of this. What we usually wind up doing is performing some kind of analysis on the structure of the code and then using that analysis to go through and try and rewrite or optimize portions of the code or optimize aspects of the code. So we'll take a little bit of a look at some of the analysis information we're going to use here and some of the ideas on how to create it. And then we'll get into much more detailed data flow analysis next week. All right, what did I want to take a look at here? The key useful pieces of information that we're going to play with over and over and over again are identifying what variables are live at the end of a block. And so the notion is a variable is live if a value has been set in it and that value is going to be used later. Right? It's going to get used before somebody else overwrites it. So the value that's there is actually going to be used. So if at the end of the block some variable is live, then we'll put that in the Liveout set for that block. So if B is our block, then Liveout B is the set of variables that are live when we leave block B. So these might be variables whose values were set in B and get used in some block that's coming after B, or it might be variables whose values were set before B started and that are essentially weren't changed by B and are going to be used sometime after B. Right? So variables values, anything that was computed in or before B that's going to be used later after B ends. So we've got this Liveout set, and that's going to get used quite a bit in terms of our optimizations, right? Trying to be aware of what information exists right now that's actually needed in the future. Then we'll take a look at the upwardly exposed variables for a block. So these are essentially the ones that the block uses that come from some previous block. So again, this is kind of the inverse idea where we're going through and saying, okay, well, what am I going to use before I set it, right? Which, if it's not getting used undefined, means that somebody previously better have set it. So these upward exposed variables of the block are the things that were set previously and that we're going to use. We might use them and then change them, but we're going to use the value that's in them coming in, if you like. And then the var kill set for our block are the set of things whose values we change within the block. So you might have a bunch of stuff in the upwardly exposed variables of B where this data is coming in, we do something with it, and then maybe we kill it. We change the value of it, right? So between these three pieces of information, we can get a pretty good idea about the flow of information into and out of a block, right? We can see what's coming into the block that we're going to need or that somebody else is going to need later. We're going to see what we change within the block, and we're going to, again, see this kind of flow through idea. All right, so this notion of Liveout, again, is going to crop up a lot in the optimizations that we take a look at here. So in terms of coming up with an algorithm to figure out what's live at the end of B, then essentially what we'll do is say, okay, well, let's start off and we'll set it just to the empty set, and then we'll try and identify values that are candidates for our Liveout. So what we can do is, again, we want to know what's going to get used by future blocks before they change it to something else, if they ever do change it to something else. So what we want to do is look at each of the successor blocks of B, so look at each of the things that comes next, and we want to go through those, and if they have an upwardly exposed variable, that means they're using something that's coming from us, whether it sort of passed through us or whether it was something that we generated. But for each of those, if they've got an upwardly exposed variable, then it's something that's produced by us or previous to us. So that goes into our live output set. The other possibility, so this is essentially capturing the stuff for those blocks themselves. The other possibility is we want to look at what's live out for them, right? It's possible that our immediate successors don't use something, but one of their successors does. So we have to capture that as well. So we'll take a look at what's the live out set for them that they don't change. So if there's something that's needed by one of their successors and they don't change it, then it needs to be in our live out set, because it's something that's coming from us or through us that's going to get used by somebody after this successor. So here's our algorithm. And again, this is essentially the approach that we want to take. And we'll take this idea and we can apply it to entire subroutines where we're trying to identify the information that's live for as the output for a subroutine. Again, we'll take these sort of two-pass approach where we'll go through, identify the entry points to our subroutine, identify the exit points, go through and figure out what our upwardly exposed variables are and what our what variables we alter, what variables or what values we set within the different blocks. And again, we can go through, we can identify these pretty easily, right? As you're going through a block, you just look at every statement. If it uses a value and you haven't set it yet, then it's upwardly exposed. If it sets a value, then that goes into the kill set. So we can do the analysis to determine this for an individual block nice and easily. One pass through, just look at the kind of statement it is. If something appears on the right-hand side of one of our statements and it hasn't been set, it's not in our var kill, then it's upwardly exposed. And if it appears on the left-hand side, it goes into our var kill. Right? So this is nice and easy to compute. And so we'll take this information, compute it for each of our blocks, and then we'll use that information, since that's nice and static, and go through and try and compute the live out. And so we'll go through and essentially update the live outs for each of the different blocks over and over and over again until we reach some kind of stable point. So this is the algorithm. Apologies for the ugly code layout here, but again, we'll go through and we've got this collection of blocks in the subroutine, and we'll just say, okay, let's start out with their live outs as empty sets. So we don't have anything in there yet. We can have the upwardly exposed variables for each of them computed. We've got the var kills for each of them computed. And essentially we're just going to go through and keep recomputing the live outs until nothing changes, until everything stays the same. So while something has changed, we'll go through this process, say, okay, let's assume nothing's changed for the moment, and then we'll go through computing the live outs, and if something changes, we'll set this to true. So for every block, we'll go through, recompute its live out, and if that's different than what its live out was prior to this pass through the loop, then we'll say, okay, something's changed. Now, the reason that these live outs change is because as we're going through the upwardly exposed variables for a block and the var kill for a block don't ever change, right? Those are nice and static. But the live out depends on the live outs of your successors, right? If you think back to this idea, if for our successors, if we look at their live out and find something that's in their live out that they didn't kill, then that's got to be part of our live out. So on that first pass through this while loop, we go through and initially compute the live out for our blocks, pretty much just based on our own information. We go through, our successor information has changed after that first pass, and so we recompute it, and that might change our live out. And so each pass, we're essentially looking one step further in the chain or the paths of blocks ahead of us, right? We're working on in the the first pass, just our information. Second pass, we're looking at information from our immediate successors. Third pass, we're getting to incorporate information from their successors. Fourth pass, we're getting information from their successors. So the liveouts change as we look further and further and further down the road, as the liveouts from more distant future blocks sort of percolate back towards us. And so eventually we reach a point where this doesn't change anymore, right? Where essentially we've computed to the end of all of the different paths that we've got out there. And eventually this stops changing, and we know what the liveout is for all of the different blocks in the subroutine. And at that point, you can turn around and say, okay, well, now I've got the liveout information for everything in here, and I can identify, the exit points from my subroutine and know what's going on for the subroutine itself. So the implications for this are that, again, anything that's in our Liveout set is stuff that are values that are going to be used by somebody else, and we want to know, essentially across the blocks, we want to know if somebody else is using this, then was it set correctly beforehand? And if nobody else is using this in the future, there's no point in keeping it around. So if we've got a bunch of values that we've computed in a block, and those values aren't in the Liveout set for the block, then nobody's going to use them in the future. I don't need to keep storing them. If I've got something that's in the Liveout set that hasn't been set yet, then we've got a problem, because then we've got uninitialized variable possibilities. And so the Liveout sets are used again, as a lot of the identification for dead code and potentially uninitialized code when we're going through and doing our analysis and optimization. One of the things that will crop up here is that the compilers have to take a kind of conservative approach when they're trying to warn you about possibly uninitialized values. All right, the compiler, when it's looking at this kind of information, right, as you've seen, we're not looking at the logic of the if-then-else statements or any of the other branching conditions to determine if something is potentially live or not. We're just looking at the paths. Is there a path where, again, ignoring the conditions under which the path is taken, is there a path along which this thing is uninitialized? If that exists, then we'll generate a compiler warning. And you've seen things like this. This is something that crops up a lot in first year, where somebody will look at their code and say, it's obviously logically clear that this code is fine, yet the compiler's giving me a warning. So if you have this kind of a situation where I say, so we'll take a look at whether a value is even or odd here. So if the value is even, then return 10. Otherwise, if the value is odd, then we'll return 20. Well, it's obvious that an integer value has got to be either even or odd. If we take it mod 2, the result is either going to be 0 or 1. So for every possible value of I, this is going to return a value. It'll either return 10 or 20. But if we go through and compile this, a compiler will typically give you a warning that you've got a path here where you're not creating a value for f to return. Right? You've got f, wherever the return value from f is being used, it's uninitialized because we haven't set a value here. And so as far as the compiler is concerned, you've got this kind of general else case that isn't being identified, where a value isn't being set. Right? This sort of implicit else. Again, logically, that can't happen. Right? Logically, we know that one of these two will be taken, but the compiler's not looking at the values in your conditions. Right? It's not trying to work out whether your conditions cover the entire possible input space. All it's doing is looking at the paths and generating a warning based on that. So, again, a little bit of why some things work the way they do when you go through and compile. All right, back to the Liveout side of things. This will get used in terms of trying to assign registers when we're doing our subroutine level allocation of register as we're going through, trying to figure out what winds up in registers and what doesn't. Obviously, if something's not live, it doesn't need to be there. This can wind up getting used in that single static assignment construction where we're going through and trying to decide names for the left-hand side variables and whatnot. Again, we can skip the steps in our SSA for values in blocks where they're not live, right? If we don't need it, then don't create it. We can go through and use that information for preventing stores to memory where they're not actually needed, right? If a value is not going to be used, there's no point in spending the time to write it back to a location to remember it. So again, this is all based on the sort of liveness of a particular value. If it's not live, we don't need it. If it is live, then we need to ensure that it's actually been filled with a valid value. All right, let's drop the Liveout for a second and move on to a different side of things. One of the other areas where we'll look at optimizations for subroutines as a whole is how we're actually going to structure those blocks. Right? Obviously, the programmer who wrote their code had this sequence of sets of instructions where, if this, then this, else this, and this while loop and this if statement inside it and this for loop inside that. But when it comes right down to it, since we're going through and we've got these tests and branches that are just saying, okay, under this condition, jump to this spot in the code, where the thing we're jumping to exists in the code doesn't really matter. So we can order the blocks in any order we like and just make sure that we're jumping to the right place when we jump to that block. Where that can matter is when we start looking at memory performance and instruction caching. So again, if we've got this idea that all of the different items in our memory are on pages in memory someplace, and the page gets brought in, when you bring a page of memory in and stick it in the cache, for instance, it's not just going to have the value that you're looking for right now. It's going to have the information in its immediate vicinity, maybe some stuff before it, maybe some stuff after it. And if that stuff includes the things that we're just about to use next, then those things are already in the cache when we get to them. So we've got improved performance. So if we can organize things so that there's a greater likelihood that when we bring one page in, we'll get a whole bunch of things that we're going to use soon, then we can get better performance, better memory performance. And again, same thing with instruction caching. If we've got instructions that we're going to use repeatedly, then it would be nice if we could have them kind of localized. So we've got this block of things that we're using over and over and over again before we have to grab something that's not in that little collection. So we'd like to organize the blocks of our code so that if there's some sequence of blocks that are frequently used together, if we quite often do block 0, block 1, block 2, we'd like them together to kind of increase the likelihood that when we bring one in, we're bringing all of them in, or we're bringing at least a chunk of multiple in. So we'll try and identify blocks that are frequently used in sequence and store them together in the executable. So we're trying to arrange the blocks in a way that best suits memory performance. So it's more important that we do this for sequences of blocks that run a lot. If you've got one sequence of B0, B1, B2 that's used 1,000 times, and this other sequence B0, B2, B4 or something like that that's only used a few times, it's more important to get that first sequence together than the second sequence. So what we'll do is identify paths of blocks and have some kind of an estimate of how frequently that particular path of blocks is used, and use that information to guide how we arrange the blocks in our final object code. So, or our final executable. So here's the idea. All we have to do is make it happen. So this notion of hot paths are the ones that are used most frequently, these chains of blocks that are used most often. So this might come through profiling the code. So maybe you compile the code originally, run some kind of utility on it to analyze which blocks of code are being used and with what frequency, so gprof or whatever it might be. Store the results someplace where the compiler can make use of it, and then compile again with the optimizations enabled so that the compiler can now look at the profiling information and say, okay, now I can come up with a better organization of those blocks. So this is a longer process for optimization, but it does give you the opportunity to rearrange things to improve performance. Again, the idea is we need to find those paths first, and once we've got them, then we'll go through and adjust our code layout. So we'll assume that the profiling's been done and that we've got information on sort of frequency of use available to us. So what we'll do is take each block and have something that indicates how frequently that block has been used, again from our profiling information. And initially we'll just say each block is a path by itself and give it some high arbitrary weight. And then what we'll do is start joining existing paths together. And the way we'll do it is by looking at the control flow graph, right? That graph that showed us which blocks lead to which other ones. And if we've got our edge information, again from our profiling, that says, you know, we went from this block to this block 37,000 times, whereas we went from this other block to this other block 12,000 times. So we've got this control flow graph. Nodes are our blocks. Edges are the transitions between them. And the edges are weighted by how often that transition was used. Then what we'll do is use that to start joining these blocks together into longer and longer paths that are heavily used, hopefully. So when we go through, we'll look at an edge that connects two blocks together. So at some point there was a transfer made from block A to block B. We'll look at the weight of it, and what we'll assign as the weight for our new longer path is the weight of the minimum of the two others and the edge itself. So the notion here is that if the first path, the initial path, had a frequency of 12 and the second path had an frequency of 200, then for our overall path we want to use the minimum of that, right? This longer path will take the smaller value because that first one is essentially the choke point, right? It only got used 12 times. And similarly, idea, if this particular edge, this transition, was only used 4 times, then we'll take the kind of minimum of this combination of values. So we'll go through starting to try and join pieces together into longer and longer paths, and for each path we'll take the minimum frequency of the pieces along that path as the frequency of the long path that we're generating. So we go through, and to do this in an organized fashion where we want to build the best paths, the hot paths, what we'll do is take all of those edges in the beginning. Right? We've got this set of blocks that are each just paths by themselves. We've got this set of edges that can connect blocks together. We'll organize those edges by their weights, how frequently those edges were used. And we'll start with the heaviest weighted edges. So if I've got an edge that was used 60,000 times and a bunch of others that were used 10, 12, 200 times, then we'll start with that 60,000 use one and say, okay, this is obviously a really heavily used one. This is likely to be part of a hot path. Right? This is, but again, one of our most traveled paths, if you like, or one of our most traveled edges. So we'll go through, we'll sort the edges by how frequently they were used, by how frequently these transitions between blocks took place. And as we're going through building the paths, we'll be pulling from this list of edges. Oops. So again, we're going through and just repeatedly looking at the paths that we've got right now, or working from the paths that we've got right now, picking the next heavily weighted edge from the list of edges we haven't grabbed yet, look at the two nodes that are on either end of them, and connect these paths together. establish a new weight for our longer path, and gradually we're joining these things together, forming larger and larger chains. What we'll do is we'll keep going through this list of edges until we can no longer find a way to combine these things. Now if you take a look at this, if I've got an edge, obviously that edge can only connect two paths together if the first path ends at the start of the edge and the second path begins after the edge. Right? So if I've got a path that ends at node 1 and an edge that goes from 1 to 3, and then a path that begins at 3, that edge can connect those two paths. So obviously as we're going through building up our paths, there are going to be fewer and fewer possible ways that we can combine things together. Right? Every time we combine two paths into a single path, we're reducing the number of available paths, and it's reducing the number of potential endpoints and beginning points for our paths. So limited number of opportunities to continue to join these things together. Eventually we'll hit a point where the edges that we've got can no longer connect any paths together, and whatever set of paths we've got left at that point is the set of paths that we'll work from. Alright, so we'll go through this process, grabbing edges, building paths, until eventually we can't combine any more paths together. Now we've got this set of, I've got a path, node 1, node 7, node 8. I've got a path that's node 2, node 3, node 4. I've got a path that's just node 5. I've got a path that's, whatever nodes I've forgotten here. Well, we've got this set of paths now, and each of them has got a weight associated with it without how frequently that path was used. And again, it's the minimum of the points along that path. So now we've got this collection of paths, each of them's got a weight, and what we would like to do is say, okay, the blocks along those paths belong together. And what we've done is taken the blocks along the high frequency path and grouped them together, and the blocks along the next highest frequency path, group them together, and the blocks along the next highest frequency path and group them together. And this is the way things have been built up. So what we'll do is lay out our code by working our way along each of the individual paths and saying, okay, write this one out, write the first one out, and the second one out, and the third one out, and the fourth one out along this particular path, and that way those things are grouped together. So we've prioritized the groupings, and we've hopefully got a reasonable structure for our layout. And again, this is going through and essentially saying exactly that. We've got our layout algorithm. We'll have the collection of paths that we want to work with. And the way we'll do it for the layout is we'll start off by saying, let's, in this collection, initially we'll just take the path that's got the start point for our subroutine in it. Right? Whatever that first block in the subroutine is, whatever that entry point is, that entry block. We'll say, let's take whatever path that one's on and throw it into our collection. And then, while there are still paths left to process, take out whatever the lowest priority path is in that collection. So right now it's just going to be that one because there's only the one in there. And then for every block on that path, we'll write it out at the end of our code space. And once we've done that, what we're going to do is go through and say, okay, for each of the blocks on that path where there's a branch essentially going to another path, let's take a look at the node, the block that's on the other end of that edge, and add that path, the path for that edge, for that piece that we've been missing so far, into the collection. So eventually we'll wind up incorporating all of the different possible paths into our collection and pulling them out by priority and writing them at the end of our blocks. So again, the idea is to try and group things together as much as possible, and hopefully this gives us a rational way, and nothing along this is terribly complex or terribly time consuming, right? It gives us a good approach for the compiler to come up with a structure, a layout for the blocks within our code, all in the hopes of optimizing our paging performance when this actually goes into execution. All right, we will leave that for now, and we'll get into whole program optimization next time around. And then again, next week we'll get into much deeper data analysis or data flow analysis to try and come up with some better optimization information.